Hello, everyone. Today, I'm going to tell you about a paper that came out in May titled Taxonomy of Branes and Infinite Distance Limits. This paper dealt with the emergent string conjecture. So today, I'm going to tell you about how the emergent string conjecture places very strong rules on the behavior of tensions of branes and masses of particles in infinite distance limits. In fact, in certain contexts, these rules only have finitely many and classifiable solutions. And in this talk, I'm going to tell you about this classification. In fact, these rules and these solutions satisfy a lot of the properties observed in the string landscape. For instance, the maximum space-time dimension of a theory is 11, just like in M theory. 11-dimensional theories will have to have zero-dimensional moduli spaces, and we'll have to have 2 branes and 5 branes, just like M theory. In 10 dimensions, you can have 1-dimensional non-compact moduli, and these theories will need to have branes just like those in 2A and 2B string theory, and the tensions of these branes will have to scale with the moduli just like in 2A and 2B string theory. So in this talk, I'm going to use the emergent string conjecture to get rules, and in certain contexts, I will be able to use these rules to bootstrap properties that theories of quantum gravity must have, and the solutions to this bootstrapping procedure will perfectly match with observations in string theory. All right, so if I have a moduli space of string vacua, and I start out at some point and consider a theory that's a very far distance from that starting point, as that theory is a really far away limit in moduli space, then that theory should be either a decompactification or a perturbative string limit. This is the emergent string conjecture of Lee, Lerche, and Weygand. So this emergent string conjecture is very sensitive to the particle tower and brane content of your theory. For one, in decompactification limits, you need to have KK modes, and in perturbative string limits, you need to have, at least in Planck units, a tower of exponentially light string oscillator modes. But the emergent string conjecture gives some more constraints than this. It forces, at least in decompactification limits, you to have to interpret the branes as being related to this decompactification and having discretized radion scalings. In perturbative string limits, I will also argue that brane tensions will have to have discretized or lattice-valued exponential scalings with the dilaton. So the emergent string conjecture will require you, in fact, to have a lot of these discretized values to be actually realized. So the emergent string conjecture will not just require particle towers and getting light in these infinite distance limits, but it will very often require also branes getting light. But they can't get light too fast. And in this talk, I will discuss these rules and these sensitive requirements. In this discussion, it is very convenient to define alpha vectors. So if I have a brane with tension T in Planck units, its alpha vector is defined as minus the gradient with respect to the moduli of the logarithm of the tension. So this alpha vector lives on the tangent space of moduli space and points in the direction where the brane gets lightest fastest. So in particular, if I'm in a situation where I have a brane whose tension in Planck units is the exponentiation of a canonically normalized modulus, then this alpha vector tells you the exponential rate. In this talk, I will consider the emergent string conjecture in very restrictive settings. So I'm going to make some assumptions. I'm going to look at just a subset of the string landscape and see what the emergent string conjecture requires of it. These assumptions can very likely be relaxed. In fact, a lot of what I'm going to tell you, the results I'll give, seem to continue to hold in theories with relaxed assumptions. But I'm going to consider theories that satisfy some strict assumptions. So these assumptions are as follows. I'm going to consider in this talk flat moduli spaces. In general, moduli spaces are not flat, but often I can consider submanifolds of moduli spaces. So in this talk, I'm going to be viewing my moduli spaces as Rn. Uh, so I'm going to assume that I can take these flat slices. So for instance, when I talk about compactifications, have in mind maybe compactifications on rectangular tori and set axions to 0. So for instance, when I talk about 2B string theory, I'll be setting the axion to 0 and talking about just the dilaton. In these flat slices, I will also assume that the alpha vectors of branes are constant. So as I move around in moduli space, the alpha vectors will continue to point in the same direction and not change in length. So this happens, for instance, for half BPS branes and maximal and half maximal supergravity. Happens asymptotically for a lot of branes with maybe relaxed assumptions, but I'm going to make these two strong assumptions and see what the emergent string conjecture forces. It turns out that with these two assumptions, the emergent string conjecture forces alpha vectors to live on lattices. Before I explain why, let me give two examples. One example is 10D 2A string theory. In 10D 2A string theory, there exists a one-dimensional moduli space, which is just the dilaton, and one can compute the alpha vectors of half BPS branes. Here they are, so D0, NS5, D2, D4, fundamental string oscillator mode, fundamental string, and D6 brane. And all of these alpha vectors live on a lattice, with lattice spacing 1 over square root of 8. Now notice this lattice isn't infinitely populated, and there are holes in this lattice, but the alpha vectors that are there reside on this lattice. In 10D2B string theory, so I'm setting the axion to 0 and just considering the dilaton, the alpha vectors of half BPS objects also lie on a lattice. So for these black dots, notice they all live on a lattice. And this lattice has, once again, spacing 1 over square root of 8. So why is this the case? Well, suppose we have a flat moduli space, so Rn. The emergent string conjecture says that as we travel in infinite distance limits in Rn, we should be in either decompactification or perturbative string limits. That means that this Rn, the coordinates of this Rn, can be thought of being either radions or dilatons. Okay, so we have this Rn. Emergent string conjecture means we can interpret the coordinates of Rn as being either radions or dilatons. So let's consider first radions. Now, if you have a radion and you start in a lowercase d dimensional theory, and you are traveling in the direction of increasing radion and you decompactify to a big D dimensional theory, well, you have some branes that get light or have some tensions that depend on this radion. And these exponential scalings with the radion from the emergent string conjecture turn out to be discretized. So suppose we have a brane with lowercase p space-time dimensions. And suppose that this brane with lowercase p space-time dimensions comes from a brane with capital P dimensions in the higher dimensional theory that you get from decompactifying along this radion. Then the component of the alpha vector of this lowercase p space-time dimensional brane in the lower dimensional theory, the component of this along this radion will be given by this formula. Or phrased differently, the dot product between the alpha vector of this brane with the direction of the alpha vector of the KK mode of this decompactification will have this discretized value. So this was for a brane that came from a wrapped or unwrapped brane in the higher dimensional theory, but this formula actually persists for other branes. In fact, in every example that I have checked, this formula, this formula here, describes radiant components of branes. And notice this is also lattice valued. So for instance, KK modes are described by this formula. So KK modes turn out to be described with lowercase p equals 1 and big P equals 0. One can just check this for KK modes or compute the radial scaling and find that little p is 1 and big P is 0. Uh, Describe the KK mode. It's a little boggling to actually think about what this means. If you take this big P seriously and this little p very seriously, what they mean, it kind of makes it look like a KK mode comes from an instanton in the higher dimensional theory, but that I'm not quite sure what that potential interpretation means. There are also some other exotic values of little p and big P that seem to describe branes where you can calculate this formula from other means. For instance, KK monopoles have little p is d minus 3, little d minus 3, and big P is big D minus 2. But that also seems a little, if you try to really understand what those numbers mean, it's a little confusing because it makes it seem like KK monopoles come from codimension 2 branes that wrap to produce codimension 3 branes in the lower dimensional theory. But the compactification manifold doesn't have enough cycles for that to work. But nevertheless, the numbers work out that way. Also, in all of the examples, there's sometimes some other kinds of branes that show up in decompactification called exotic branes. In all of the known examples, exotic branes are also governed by this formula. So in what goes forwards, I will assume this radion lattice condition. And I present this formula in the paper. In these flat moduli spaces, in addition to radions, you can also have dilitons. And in fact, it turns out that the components of alpha vectors of branes in dilaton directions are also lattice valued or quantized. So in particular, if I have a dilaton direction, or equivalently the direction of an alpha vector of a string or its oscillator, the alpha vector of a little p minus 1 brane has a component in the direction of the dilaton given by this formula. So p is the spacetime dimension of the brane, little p is the spacetime dimension of the brane, and big P is an integer. The way to derive this formula, or the way I derive this formula in the paper, is by considering an emergent string limit, then putting my theory on a circle, t-dualizing, then viewing the winding mode of the string as being a KK mode in the lower dimensional theory, then applying the radial lattices condition to that KK mode in the lower dimensional theory, then undoing the t-duality, and then decompactifying to my original emergent string limit. And I derive this dilaton lattice condition in that way. All right, so I have these two lattice conditions. They get kind of interesting in higher dimensional moduli spaces. So consider, for example, a two-dimensional moduli space. So suppose I have that this up direction is a radion, let's say. And suppose that this black dot here, 1 subscript 1 comma 0, suppose that's a KK mode, the alpha vector of a K mode. Now, from the radion lattice condition, if I have alpha vectors of other branes, so maybe in this case particles and strings, they need to have lattice valued dot products. Their alpha vectors need to have lattice valued dot products with this KK mode, given by the radion lattice formula presented on the previous slide. Now, suppose, so they need to lie on these green lines. Now, suppose I have another KK mode, let's say this one right here, that gets light in the same duality frame, let's say, as this KK mode. Now, these alpha vectors of these other objects, of the alpha vectors of the branes in the theory, need to also have discretized or lattice valued dot products with this KK mode. So the alpha vectors of the other branes need to lie on these red lines. But in order for this to be true for both this KK mode and this KK mode, the alpha vectors of branes need to lie at the intersections of these magenta and red lines. And so in this 2D example, alpha vectors of branes need to lie on a 2D lattice. And in fact, in my paper, I generalize this, so to higher dimensional cases as well. So in particular, if I have an alpha vector of a brane with lowercase p space-time dimensions, and I want to find out where on a lattice it lives. And suppose I have a collection of KK modes that get light in a common duality frame. And suppose that each KK mode uh, corresponds to decompactification from lowercase d dimensions to big D subscript I dimensions. And suppose that each alpha vector, or the p minus one brane I'm considering, has a uh, in the radion lattice formula has a big P that is P subscript I for the ith KK mode. Uh, then the alpha vector of this brane is forced to be governed by this formula. So I derived this formula in my paper. So this formula tells me the positions allowed for various branes. Um, so it's fixed by the number of space-time dimensions of the brane, but also it's given by this vector P, which tells you the big P for each KK mode. So with this formula, you can then compute this sort of generalized, this gives you formulas for what the lengths of various alpha vectors need to be. It gives you some dot product rules that various alpha vectors need to satisfy. In a paper from 2024 with Ignacio Ruiz, Irene Valenzuela, Ben Heidenreich, and Tom Ruidelius, we found several dot product formulas for KK mode, for towers that get light in a particular duality frame. We found some formulas for dot product relationships between the lightest towers. This formula here generalizes this to heavy towers, but also generalizes it to alpha vectors of branes as well. In my paper, I also derive an analogous formula for when one of these alpha vectors is, instead of being a KK mode, is a string oscillator mode. There's a similar formula in the paper. So this forces the alpha vectors to live on a lattice. But this formula doesn't tell you how populated this lattice needs to be. Well, this lattice can't be completely populated. That would give you branes that get too light too fast. You know, having a long alpha vector means the brane would get light very fast, and that could destroy the emergent string conjecture if the brane gets light too fast. But you need to have sufficiently many alpha vectors for the emergent string conjecture to be satisfied. Even the sharpened distance conjecture. So for instance, the sharpened distance conjecture requires that the convex hull of alpha vectors of particle towers contains the origin-centered ball of radius 1 over square root of little d minus 2. So for instance, this blue circle, maybe in this particular example, needs to be contained in the convex hull of alpha vectors of particle towers. In my paper, I identify a way to find out whether a lattice site needs to be populated. I identify this. So in particular, I identify the following condition, that if this condition is met, then the lattice site for a p minus 1 brane needs to be populated by a brane, by the emergent string conjecture. So this condition is a sufficient condition for a site to be necessarily populated. So this condition has two parts. Part one, I call the norm condition. So this is a condition on the length of an alpha vector. So this part one is satisfied if the length of the alpha vector satisfies this equation where n is an integer. So this turns out to be a Diophantine equation on the lattice. And it only has finitely many solutions because the solutions have to be restricted to an annulus. And there are only finitely many lattice points that ever exist in an annulus. This condition is related to the winding mode of the brane being a KK mode that decompactifies to an integer number of space-time dimensions, integer n number of space-time dimensions in a duality frame. The second part of the ESC requirement is this product condition. So this product condition is that every other emergent string required Q minus 1 brane, where Q is less than or equal to P, has an alpha vector whose dot product with the alpha vector of the brane you're the site you're considering is bounded above by this value. So if you have a q minus one brane and its dot product is larger than this, then perhaps the q minus one brane could save the emergent string conjecture under compactification. But if you don't have this, then then your site it needs to be populated. So with these two conditions, you can then diagnose. So if these two conditions are met for a lattice site, you know that that lattice site needs to be populated by the emergent string conjecture. So then you can do a classification procedure. So here's how this works. You start out with a duality frame, so some towers getting light, and they define a lattice. Then you look at all of the allowed positions of particle towers in a way where the sharpened distance conjecture is satisfied, or emergent string conjecture in that space-time dimension is satisfied. So you find out all of the allowed tower polytopes. And then from there, you then look at this, and then you can find out all of the allowed strings. So for each consistent tower polytope, you then consider all of the lattice points for strings and see which ones are required from the emergent string conjecture. Then you have now the particle towers and the strings for each solution. You can then find out what 2 branes are needed. And then you can find out what 3 branes are needed and 4 branes. So you can actually classify all of these solutions to these ESC requirements. And it turns out there's only a finite set of solutions. So it turns out this only works if the space-time dimension is at most 11. If you had space-time dimensions of greater than 11, you would run into problems under dimensional reduction or S-duals of strong coupling limits of dilitons the spacing would be too wide for you to get consistent theories. So in this classification, the space-time dimension must be at most 11. You can also, I discussed this in depth in the paper, but 11D theories have to have 0-dimensional moduli spaces. And if you have 1D moduli spaces, the highest space-time dimension is 10 for that. In my paper, I argue for these maximum space-time dimensions. And with these maximum space-time dimensions, there are only finitely many solutions to these ESC requirements. In my paper, I found all of these solutions for moduli spaces of dimensions 0, 1, and 2. I could have gone more. I could have gone to higher dimensional moduli spaces, but the paper was already over 100 pages long, so I stopped at 2D. And now I will present some of the results of this classification. Let's start with 0D moduli spaces. So in 0D moduli spaces, all of the alpha vectors have to have length 0. So you can study these ESC requirement conditions on the lattice site where the alpha vector is just 0. In 11D, the emergent string conjecture requires you to have branes with 3 space-time dimensions or 6 space-time dimensions. In other words, it requires 11D theories with 0-dimensional moduli spaces to have 2 branes and 5 branes. This is just like M theory. M theory has M2 branes and it has M5 branes. In 10D, the emergent string conjecture requires theories with 0-dimensional moduli spaces to have strings, 3 branes, and 5 branes. This is just what you get when you quotient the 2B string theory by SL2Z and just get a point moduli space. And you can consider and interpret the same sort of classification of 0D moduli spaces in lower dimensions. Let's move on to 1D moduli spaces. Now, the highest space-time dimension where this classification works is in 10D. The highest space-time dimension where you can have a 1D moduli space is in 10D. Now, you might think, okay, I could have a 10D theory with 2 emergent string limits, or 1 emergent string limit, 1 decompactification limit, or 2 decompactification limits. It turns out that the 2 decompactification limits is forbidden with this classification. In my paper with Irene, Ignacio Ruiz, Tom Rudelis, and Ben Heidenreich, we were using slightly weaker assumptions, and and we did not rule that out with those assumptions. But with these strong lattice rules, that example is ruled out. So in 10D moduli, in 10D theories with 1D moduli spaces, um, there are only two kinds of theories. And there are only two solutions to these equations. So one solution has decompactification in one direction, an emergent string limit in the other direction. And the branes that the emergent string conjecture thrusts on you are as follows. So in the decompactification limit, you have the KK mode. You have a 5-brane, you have a 2-brane, you have a 4-brane, you have a string, you have the string oscillator modes, and you have a 6-brane. This is exactly like 2A string theory. 2A string theory is the D0, NS5, D2, D4, fundamental string oscillator, fundamental string, and D6 brane. But I'm not starting with 2A string theory. I'm just starting with what the emergent string conjecture requires of a 10D theory with a decompactification and emergent string limit. The emergent string conjecture forces you to have this. So just with the emergent string conjecture, you bootstrap this figure, and this exactly matches 2A. There's another solution in 10D. This is a theory with two emergent string limits. The emergent string conjecture forces you, and these like taxonomy rules, or force you to have these branes. So a 7-brane, a 5-brane, string oscillator, 3-brane, string oscillator, 5-brane, string, and 7-brane. This is exactly the dilettante profile when you set the axion to 0 of the half BPS branes of 2B string theory. So just starting with the emergent string conjecture and these taxonomy rules, you bootstrap this non-trivial brane structure of 2B string theory. Or phrased differently, if I slightly changed the formulas of the tensions in 2B string theory or deleted a brane, I would get failure of the emergent string conjecture upon compactification using the assumptions I'm using. It is intriguing, I should mention. It is possible maybe to relax the assumptions I'm using. And so there are these unique two solutions in 10D string theory. Maybe with relaxed assumptions, you could argue that heterotic string theory needs to some extent fit under this structure. And if so, maybe you could predict new branes. Although heterotic string theory does not satisfy the assumptions I'm using. So work needs to be done to make definitive statements in that context. All right, you can look at this in lower dimensions as well. So in 10D, there were two examples of 1D moduli spaces, two solutions. One was 2A-like and one was 2B. In 9D, there's only one solution, which is this one. Intriguingly, you get this solution when you put M theory in a 2 torus and just vary the volume of the 2 torus. This is exactly the configuration of alpha vectors of half BPS branes you get in that context. In 8D, there are two solutions. In 7D, there are two solutions. In 6D, there are 4 solutions. In 5D, there are 4 solutions. I should mention that these figures also show up in theories with relaxed assumptions. So for instance, this 5D example shows up in examples in 5D n=1 examples, actually. Also in the 10D examples, the known branes in heterotic string theory are all governed by these positions. In 4D, there are 7 solutions, and in 3D, there are 9 solutions. So we have now classified all 1D moduli spaces. Let's now classify and bootstrap 2D moduli spaces for theories satisfying my assumptions. It turns out so in 2D, you can consider different lattices. One lattice you get from 2 KK modes, each one decompactifying to 10D. You can also get a lattice from a KK mode and a string oscillator mode. And there are 2 different solutions you get with the KK mode and string oscillator mode. So in principle, you have at least 3 different Tower polytopes. But it turns out all of these Tower polytopes are congruent. There's only one Tower polytope. Furthermore, all of the branes of the emergent string conjecture are, the brane structures are all the same from all these different lattice approaches. So in 2D, in 9D, there's only one unique solution you get, which is this figure. So here I've drawn KK mode decompactifying to 10D and KK mode decompactifying to 10D. you're forced to have a particle down here. So this triangle here, you get this triangle uniquely, but you also are forced to have a string here, four brane here, four brane here, two brane here, three brane here, five branes here, here, and here, and seven branes here, six branes here and here. This is exactly what you get when you put two-way string theory on a circle and have the axion 0 and just consider radion dilaton, or put 2b on a circle and consider radion dilaton with axion 0. So you get just one unique thing. So this taxonomy program, in a sense, knows about the duality between 2A and 2B string theory. But this is bootstrapped. I will keep repeating. I am not starting with like the structure of or I'm not starting with 2A or 2B string theory and finding this. I'm starting with the emergent string conjecture. And my assumptions, which I must say are inspired by what happens in string theory. But I'm starting in principle just with assumptions, these simple assumptions about the emergent string conjecture, and rederiving this structure from string theory. I would also like to point out, this will be relevant for the next slide, but these shaded regions are related to the brane distance conjecture, and these circles are the convex holes that need to be enclosed in the relevant regions. So brane distance conjecture is satisfied in this example. It will be satisfied on the next slide for the next examples. I've also plotted in cyan the species polytopes, and these red dots are the alpha vectors of the mass scales of the non-particle branes. So for consistency, these alpha vectors of these red dots can't be outside of the species polytope. But intriguingly, in this example, there's a pattern happening where all of the alpha vectors of these red dots are exactly on the boundary of the species polytope. I should also mention, I also bootstrapped, in this case, I guess, the species polytope. Now, the species polytope and this tower polytope were bootstrapped, I should say, in the taxonomy paper from 2024 with myself, Nacho Ruiz, Ben Heidenreich, and Tom Rudelius, and then Renan Valenzuela. But in the next slide, I will eliminate some theories that were considered, or some theories that were considered in that first paper with weaker assumptions will not be consistent with the assumptions I'm using here. All right, so let's look at more examples. So I showed you just this 9D example. In 8D, there are two examples, and I've checked. These two examples actually show up in maximal supergravity. So this is giving you quite detailed and non-trivial brane structure, but from the emergent string conjecture, but this also shows up in max sugra. In 7D, there are two solutions. In 6D, there are four solutions. So here's where there's this difference between the first taxonomy paper and this. In the first taxonomy paper, we used weaker assumptions, but these lattice rules, so we used weaker assumptions and found more tower polytopes in 6D. In this case, a lot of those tower polytopes are not consistent with the assumptions I'm using here, and there's a reduced list of theories consistent with my assumptions. In 5D, there are 5 solutions. 4D, there are 9 solutions, and 3D, there are 12 solutions. So this is just bootstrapping and classifying all of these solutions. So it's classifying the tower polytopes, the brane alpha vectors, and also it's classifying the species polytopes. I could have gone to higher dimensional theory, moduli spaces, but I stopped at 2D. That's work in progress. Also, I've checked many of these polytopes show up in maximal supergravity. It's possible that all of these show up in maximal supergravity, but showing that is non-trivial. It requires finding all possible 2D slices of the polytopes you get in M theory or maximal supergravity examples. And to compare that with this is work in progress. So I mentioned briefly, perhaps the assumptions I'm using can be relaxed and maybe can predict new branes. It's also fun to apply these rules to, for instance, the theories with extra space, with large extra dimensions. So for instance, you could apply this taxonomy program to the dark dimension scenario. I mean, this is requiring what I'm doing is speculative. It's possible that the assumptions I'm using wouldn't apply in the dark dimension scenario. But suppose they did. What would you get? Well, it turns out that that in large extra dimension scenarios, this classification often requires the existence of um, extra branes, sometimes or strings, for instance. This is related to having the emergent string conjecture hold when you compactify our universe to 3D. So, for instance, in the dark dimension scenario, if you consider the situation where you have at least one extra modulus, um, these ESC requirements or this classification always requires there to be a string, and the string needs to come from a string in the 5D theory, and you can fix where its alpha vector has to be. And you can argue that the mass scale of the string is less than or equal to, or is bounded above by the scale of the third root of the KK mode from the extra dimension. And if you plug in the values, let's say in the dark dimension scenario, this bounds the mass of the string to be below or comparable to the 12th root of the cosmological constant in Planck units. So this is just an application. There exist other applications as well. Um, in conclusion, for flat moduli spaces with constant alpha vectors, the emergent string conjecture requires these alpha vectors to reside on and sufficiently populate lattices. I found all ESC consistent solutions to these requirements in 0D, 1D, and 2D moduli spaces, and reproduced a lot of structure already observed in string theories that also satisfy these assumptions. My assumptions can likely be relaxed. Perhaps you only need to have these assumptions asymptotically in moduli space. And in many examples, theories that don't satisfy my assumptions still have this lattice structure asymptotically. Perhaps with relaxed assumptions, you could predict new branes, maybe branes in dark dimension scenarios, maybe new branes in heterotic string theory. Maybe one could make contact with cobordism conjecture, which also implies new branes. Maybe there's some strong conjecture that combines cobordism and emergent string conjecture. Thank you.